Thank you, Professor Olsson. Now, Professor Mats Larsson will give a more detailed presentation of the prize. Please, Mats.
Thank you. Yes, this year's Nobel Prize in Physics is about science at the time scale of attoseconds. And what you see here is an attosecond related to 1 second, which is approximately the heartbeat. And the ratio of 1 second to an attosecond is the same as the ratio of the age of the universe expressed in seconds to 1 second. And as Professor Olsson explained, we are now in the world of electrons. And let me remind you, electrons are not only working in gadgets like this. They are working in your full body. Chemical reactions are controlled by electrons, and they move on a time scale of attoseconds. This is the beginning. This was an experiment carried out in Paris-Saclay in 1987 by Nobel laureate Lullier and co-workers. And what they did here was they took a very powerful infrared laser and shine it through a gas jet of neon or argon or xenon. And then they looked at the photons coming out from this interaction with a spectrometer, as you can see here. So this is actually the original drawing of their experiment in the 1980s. So what did they see? Well, they saw a number of, the laser has a base frequency. It's about 1,000 nanometer in wavelength. And they saw overtones of this frequency, a large number of overtones. And the overtones first fell off quite rapidly, and then came a long plateau, and then a cutoff. So the question was, what is generating this plateau, and how can it be exploited? And Lullier in particular worked for a decade with different theoretical and experimental methods to understand what this plateau can be used for and how to explain it. So in order to generate very short pulses, you need all these different overtones. And I will illustrate this now by assuming that we have a number of light. We have light with different frequencies. As you can see here, light with different frequencies. And if we now let these different frequencies interact and interfere, what can happen is that they interfere in such a way that at certain points we create an amplification, whereas at many other points there is destructive interference, nothing happens. And what you get is a pulse train of attosecond pulses. So the trick is really to sum up many different overtones. That gives you the bandwidth. But that's for one atom. Now we are talking about several atoms, and several atoms must work together in phase. Otherwise, it won't work. And it's the same with the symphony orchestra. If each member of the orchestra would be playing whatever they want, the audience would just experience noise. But if they play in sync, and of course you have the conductor making them play in sync, then we get music. And it's the same with the atoms. They have to work in sync. And this was figured out by Lullier and others, how to do this. Here is an example of an experiment, attosecond experiment. And this gives you a little bit of a feeling for the length scale of such an experiment. It's not an enormous big experiment. And what you see down here in the corner is laser light, let's say infrared laser light coming in. The laser beam is divided in two parts. One part goes to the left and then into the gas jet where you produce attosecond pulses. The other part goes into a delay line so that you can shift the time difference between the attosecond pulses and the infrared pulses. And then you combine them on a mirror and send them into your experiment. And out comes electrons that you can observe. And this was the technique, or a similar technique, that was developed by Nobel laureate Pierre Agostini. He developed something called the rabbit technique. He could show that he could not only produce attosecond pulses, but he could also measure the width and they turn out to be 250 attoseconds. And this experiment was done in Paris, Saclay, in 2001. Almost at the same time, the other laureate, Ferenc Krauss, developed a streaking technique, which is a little bit different, but similar principle. And he produced so-called isolated attosecond pulses, 650 in pulse width. And this was done in Vienna in 2001. And these two platforms are the existing platforms in attosecond physics up to this day. Of course, the experiments have been improved much, but it's basically these two different techniques that are in use. And the choice, RABBIT, which stands for reconstruction of attosecond beating by interference of two-photon transitions. But so depending on the application, you decide, do you want to use a pulse train with the RABBIT technique, or do you want to use isolated pulses with the streaking technique? And what you can see here is that you have the attosecond pulses overlap with infrared probe pulses, atom ionization, the electron coming out, and you get a signal which is a replica of an attosecond pulse. So by measuring this electronic signal, you can get an understanding of what is the pulse width. What can you do? Well, here is an example of how one can study photo emission delay. The question here arises. Let's take a neon atom. Let's expose it to an attosecond pulse. And the question is, if the electron is in the 2s, more tightly bound in the atom, or if it's more loosely bound, like a 2p electron, do they come out with at the same time? No, they don't. It was actually possible to figure out, by doing these experiments, that one electron goes faster out by 20 attoseconds. An incredibly short time that was actually possible to measure. And this was an experiment done in Lund. So let's go to applications, because I know that you will ask about that. With the attosecond physics and science, we have come to the point where we can have localization control of electrons in a molecule. This is a new field that can be called attochemistry, where you can locate electrons in a molecule and you can figure out what they are doing, jumping around. Ultrafast switching from insulator to conductor. This is a dielectric material, for example, silicon dioxide. You can switch with an attosecond pulse between a situation where this dielectric is not conducting, it's an insulator, but in 1 femtosecond, you increase the conductivity by 18 orders of magnitude. And of course, this is an important field because it gives you possibilities to develop very fast electronics based on these short pulses. And the final example, which is now being pursued by Ferenc Krauss now in Garching, is molecular fingerprinting applied to biological samples. So what is this? Well, you have a blood sample. You expose it to a very short infrared pulse. This infrared pulse will vibrationally excite the molecules in the blood sample. And there are literally thousands of molecules in this blood sample. And then they emit infrared, and you detect this. And by analyzing what you detect, you can, and doing this with attosecond precision, you can draw conclusions whether there has been any change in the blood sample. So the idea here is not to analyze all the 1,000 molecules, but to find small, minute changes. And by doing this, there is the hope in the future that you will be able to capture whether a person have developed, for example, lung cancer in the body, so that you have a very sensitive method. And if you can diagnose cancer at a very early stage, treatment will be much more successful. So this was just a few examples, and I'm sure that you have a chance to ask the Nobel laureate afterwards. So I thank you now for my presentation, and we have them here again. Pierre Agostini, Ferenc Krauss, and André Lie. for experimental methods that generate attosecond pulses of light for the study of electron dynamics in materials, in matter. Okay, thank you.
Thank you, Professor Larsson. Now we shall see if we have one of the laureates online. Professor Anne Luer, are you with us on phone from Lund?
Hello, yes. Can you hear me?
I can hear you. Good day, Professor Luer.
Hello.
Can you hear us?
Yes.